What if I told you that 73 hours ago, an asteroid the size of a football field passed between Earth and the Moon? And we didn't see it until it was already past us. Not a distant flyby. Not a predicted close approach. Not something astronomers had been tracking for months. This asteroid, designated 2025 UX14, came from the direction of the Sun, hidden in the glare, invisible to our telescopes, and we only discovered it existed 11 hours after it had already made closest approach at just 238,000 kilometers. That's 62% of the distance to the Moon. That's closer than hundreds of our own satellites. If it had hit us, if its trajectory had been just slightly different, if it had arrived 6 hours earlier when Earth was in a different position, it would have struck with the force of 400 Hiroshima bombs. An entire city gone, millions dead, and we would have had zero warning. Zero time to evacuate, zero chance to deflect it. November 23, 2025, 1447 UTC. An automated survey telescope in Chile captured images of a fast-moving object. The software flagged it as unusual. High velocity, wrong direction. Trajectory calculations showed it had just passed Earth. Hours ago, while we were looking the other way, the object was 140 meters across. Rocky, dark, low albedo, moving at 32 kilometers per second relative to Earth. It had approached from only 18 degrees away from the Sun's position in the sky. That meant it was visible only during twilight, only for brief windows at dawn and dusk, and only if you knew exactly where to look, which nobody did, because nobody knew it existed. For 11 hours, an asteroid capable of destroying a major city was closer to Earth than the Moon, and humanity was completely unaware, going about normal life, working, eating, sleeping, while a cosmic bullet passed silently through our neighborhood, missing us by cosmic chance, not by preparation, not by detection, just by luck. This isn't the first time. In 2013, the Chelyabinsk meteor exploded over Russia with the force of 30 Hiroshima bombs, injured 1,500 people, damaged thousands of buildings. Nobody saw it coming. It came from the Sun's direction, hidden until impact. In 2019, asteroid 2019 OK passed Earth at 0.19 lunar distances, closer than 2025 UX14, size 100 meters, detected less than 24 hours before closest approach. If it had hit, it would have been catastrophic. And we almost missed it entirely. And now 2025 UX14, the closest undetected approach in recorded history, coming from the Sun. The blind spot, the direction we can't watch because looking at the Sun destroys telescopes, the vulnerability in our planetary defense system, the gap that could kill millions. NASA estimates there are 25,000 near-Earth asteroids larger than 140 meters. We've found about 10,000 of them. That means 15,000 are still undiscovered, still out there, potentially on collision courses, hidden, invisible, waiting. And some of them, maybe hundreds, maybe thousands, are approaching from the Sun's direction, where we can't see them, where our detection systems are blind. If you want to fall asleep learning about the asteroid that almost killed us, why it wasn't detected, how many more like it are hiding in the Sun's glare, what plans exist to fix this terrifying blind spot, and what would happen if the next one doesn't miss, subscribe right now. Every week we explore cosmic dangers that are real, immediate, and closer than you think. This isn't science fiction. This is the reality of living on a planet in a cosmic shooting gallery. And we're not watching all the directions the bullets can come from. Let's investigate why we almost died and didn't even know it. November 23, 2025, 1447 UTC. The Atlas telescope at Cerro Tololo Inter-American Observatory in Chile was conducting its nightly survey. Atlas, Asteroid Terrestrial Impact Last Alert System, scans the sky automatically. 4 telescopes, 2 in Hawaii, 1 in Chile, 1 in South Africa, working together, covering the whole sky every 24 hours, looking for moving objects, asteroids, comets, anything that might threaten Earth. The Chilean telescope captured 4 images of the same patch of sky, separated by 30 minutes between each image. Standard protocol. Comparing images lets you see what moved. Stars don't move noticeably in 30 minutes, but asteroids do, and fast-moving objects move a lot. The automated software compared the images, identified objects that appeared in different positions, calculated their motion, flagged anything unusual, and at 14:47 UTC, it flagged something very unusual. Object moving at 2.4 degrees per hour. That's extremely fast for an asteroid. Most move much slower when they're far away. Fast motion means close, very close. Either that, or it's something else entirely. Satellite. Space debris. Instrumental artifact. Dr. Richard Kowalski was on duty at the Atlas Science Operations Center in Hawaii. He received the automated alert, pulled up the images, examined the object. It was faint, magnitude 18, barely visible even in Atlas's sensitive cameras, but definitely real, definitely moving. And moving fast, he ran preliminary orbit calculations, input the position and velocity. Let the software project the trajectory. Where was this object? Where had it come from? Where was it going? The results made his blood run cold. The object had made closest approach to Earth 11 hours ago. At Aero 323, UTC, distance 0.62 lunar distances, about 238,000 kilometers. It had already passed us, already missed us, and they were only discovering it now, after the danger had passed. "Oh my God," Kowalski said aloud. "We missed one. We missed a big one." He checked the size estimate based on brightness and estimated albedo. Diameter, approximately 140 meters. Uncertainty, plus or minus 30 meters. But definitely in the range of 170 meters. That's city killer size. That's catastrophic if it hits. That's exactly the size of asteroid we're supposed to be finding years in advance. And they'd found it 11 hours late. He immediately escalated. Sent alerts to NASA's Center for Near-Earth Object Studies, to the International Astronomical Union's Minor Planet Center, to ESA's Space Situational Awareness Office, to planetary defense coordinators worldwide. Marked urgent, marked critical. This was a failure, a near miss we hadn't seen, the kind of event that keeps planetary defense experts awake at night. Within 30 minutes, telescopes worldwide were repositioning, confirming the object, refining its orbit, characterizing its properties. By 16 Quat UTC, 5 different observatories had confirmed 2025 UX-14. The orbit was solid. The size estimate refined to 140 meters, plus 20 meters. And the question everyone was asking, how did we miss this? Dr. Paul Chodas, director of CNEOS at NASA's Jet Propulsion Laboratory, held an emergency briefing at 18 UTC. "We've confirmed a close approach that occurred this morning at 3:23 UTC. The object, designated 2025 UX-14, passed at 0.62 lunar distances. This is within the detection threshold we're supposed to achieve. We should have seen this days in advance. We didn't. We need to understand why." Dr. Amy Meinzer, principal investigator for the Near-Earth Object Surveyor mission, reviewed the trajectory. It came from the sun's direction. Approach angle was 18 degrees solar elongation. That means it was only visible during twilight, dawn and dusk, and only for about 45 minutes per day. Outside those windows, it was in the glare, invisible. "Atlas scans the sky every 24 hours, she continued. "But it can't scan during daylight. It can't point at the sun. None of our telescopes can. So there's a cone around the sun where we're blind, about 45 degrees radius. Objects in that cone are invisible until they emerge from the glare. By then, they might be very close. Like this one." Dr. Chodas pulled up statistics. "We estimate about 30% of near-Earth asteroid approaches come from solar elongation angles less than 45 degrees. That means 30% of potential impactors approach from directions we can't easily monitor. This is a known vulnerability. We've known about it for decades, but we haven't fixed it. And 2025 UX-14 just demonstrated why we need to fix it. Because next time, we might not get lucky. The media learned about the near miss by 20 Kwaun Sahun Situatetichin Sinkituin. UTC, Asteroid, passes Earth undetected until after closest approach. City killer asteroid came from Sun's direction. Near miss exposes planetary defense blind spot. The headlines were alarming but accurate. This was a failure, a gap in our defenses, a vulnerability that could kill millions if exploited by bad luck. November 24, 2025. Dr. Marina Brozovic at JPL was leading the detailed characterization effort, using radar, using spectroscopy, using photometry, trying to understand everything about 2025 UX-14. What was it made of? How was it shaped? How fast was it rotating? Every detail mattered for understanding future threats. The Goldstone radar in California tracked the asteroid as it receded from Earth, bouncing radio waves off it, measuring the echoes, building up a picture of its shape and spin. The data revealed a contact binary, two lobes stuck together, like a peanut or a snowman, two roughly spherical chunks in contact. Common shape for asteroids suggests gentle collision in the past. Two objects that touched and stuck. Dimensions: 140 meters long, 80 meters wide. Rotation period: 4.2 hours. Tumbling chaotically. Not a nice simple spin. Complex rotation about multiple axes. That's also common for contact binaries. The uneven mass distribution creates complicated dynamics. Spectroscopy showed the composition. Carbonaceous. C-type asteroid. Dark. Low reflectivity. About 5% albedo. That explained why it was so hard to see. Dark asteroids reflect less sunlight, appear dimmer, are harder to detect, especially from far away, especially when approaching from the sun's direction where you're already struggling against glare. This is one of the stealthier asteroid types, Dr. Brozovic explained to the team. Carbonaceous. Dark. Small by cosmic standards, but large enough to cause regional catastrophe. If this had hit, it would have released about 350 megatons of energy. For comparison, the largest nuclear weapon ever tested was 50 megatons. This would have been 7 times more powerful. The impact effects depend on where it hit. If it struck ocean, massive tsunami. Coastal devastation for thousands of kilometers. If it struck land, crater about 2 kilometers wide. Everything within 30 kilometers destroyed by blast wave. Everything within 100 kilometers severely damaged. If it hit a city, millions dead. And we had no warning. None. We discovered it after it had already passed. Dr. Lindley Johnson, NASA's Planetary Defense Coordination Office Director, analyzed the trajectory more carefully, looking at Earth's position when the asteroid passed. Looking at where Earth would have been at different times. How close did we come to disaster? The asteroid passed at 0323 UTC. Earth rotates 15 degrees per hour. That's 1,600 kilometers at the equator. If the asteroid had arrived 6 hours later, Earth would have rotated 90 degrees. Different hemisphere facing the asteroid, different potential impact location, but more importantly, Earth's orbital motion. Earth moves about 30 kilometers per second in its orbit around the Sun. In 6 hours, Earth travels 650,000 kilometers. The asteroid passed at 238,000 kilometers. If it had arrived when Earth was in a different position along its orbit, the distance could have been much closer, or much farther. The timing mattered enormously. "We got lucky," Johnson said bluntly. "If this asteroid had been on a slightly different trajectory, if it had arrived at a slightly different time, it could have hit. And we would have had no warning. The last thing anyone would have seen was a bright flash. Then blast wave. Then destruction. No alerts, no evacuation. No defense. Just impact." He pulled up simulations. showing what would have happened if 2025 UX-14 had struck. Different scenarios, different locations, all catastrophic. Scenario 1. Ocean impact. Pacific Ocean between Hawaii and California. Tsunami waves 30 meters high propagating outward, reaching Hawaii in 2 hours. California in 5 hours. Japan in 8 hours. Coastal devastation. Millions at risk. Economic damage in hundreds of billions. Scenario 2. Land impact. Rural area. Crater 2 kilometers wide. 400 meters deep. Everything within 30 kilometer vaporized. Everything within 50 kilo destroyed by blast. Everything within 100 kilometers damaged by heat and shockwave. If this happened in sparsely populated area, maybe few thousand casualties. But still, enormous local devastation. Scenario 3. City impact. Major urban area. Direct hit on metropolitan region. Everything within 30 kilometers destroyed. That's the entire urban core of most major cities. New York, London, Tokyo, Shanghai, Delhi, Los Angeles, São Paulo, any of them. Millions dead immediately. Millions more from secondary effects. Fire, collapse, chaos, civilizational trauma. This is what we're trying to prevent, Johnson said. This is why planetary defense exists. Not because asteroid impacts are common, they're rare, but because the consequences are so severe that even rare events must be prevented. And we can prevent them. We have the technology. We proved it with DART mission. We can deflect asteroids if we find them early enough, but we can't deflect what we don't see. And we didn't see this one until it was too late. November 25, 2025. Dr. Amy Meinzer held a press conference to explain the fundamental problem. Why had 2025 UX-14 gone undetected? Why was the sun's direction such a vulnerability? And what could be done about it? She started with basics. Earth-based telescopes can't look at the sun. The sun is too bright. Looking directly at it would damage or destroy the telescope's sensors. So there's a region around the sun we can't observe, roughly 45 degrees radius. That's a large portion of the sky, and asteroids in that region are invisible to us. Now, most asteroids aren't in that region most of the time. They orbit the sun. Sometimes they're east of the sun as seen from Earth. Sometimes west, sometimes north or south. They move in and out of the solar glare, so we can usually see them when they're outside the glare zone. But asteroids approaching Earth from the sun's direction stay in the glare until they're very close. That's when they're most dangerous and least visible. She pulled up diagrams showing Earth, the sun, asteroid trajectories. Some asteroids approached from the night side, easily visible. Weeks or months of advance warning possible. Other asteroids approached from the day side, hidden in the sun's glare. Visible only during twilight, if at all. Minimal warning time. About 30% of potentially hazardous asteroid approaches come from solar elongation less than 45 degrees, Meinzer continued. That means nearly a third of potential impactors approach from directions where our ground-based detection is compromised. We've known this for decades. The Chelyabinsk meteor in 2013 came from the sun's direction. We didn't see it coming. 2019, came from the sun's direction. We almost missed it. And now, 2025 UX-14. Another near miss from the blind spot. The solution is to observe from space, she said. Put a telescope in orbit where it can look toward the sun without the sun damaging it. Use infrared detection. Infrared works better than visible light for asteroid detection because asteroids emit their own infrared radiation. They're heat. They don't just reflect sunlight. So even against the bright background of the sun, infrared telescopes can detect asteroids. She showed the design for NEO Surveyor, NASA's Near-Earth Object Surveyor mission. Infrared Space Telescope, launching in 2027, will orbit at L1 Lagrange point, between Earth and Sun, looking back toward Earth's orbit, detecting asteroids as they approach, finding them months or years in advance, even the ones coming from the Sun's direction. NEO surveyor will find 90% of near-Earth asteroids larger than 140 meters within 5 years of operation, Meinzer explained, including the ones that approach from the Sun. It will close the blind spot, make us safer. But it doesn't launch until 2027, 2 years from now. Until then, we're vulnerable. We have incomplete coverage, and events like 2025 UX-14 can happen again. A reporter asked, "How many more asteroids like 2025 UX-14 are out there right now, approaching from the Sun's direction, that we don't know about?" Meinzer paused, chose her words carefully. "We estimate there are about 15,000 undiscovered near-Earth asteroids larger than 140 meters. Of those, roughly 30% approach from directions that make them hard to detect from the ground. That's about 4,500 asteroids. Some of those are currently approaching Earth from the Sun's direction. We don't know how many. We don't know which ones. We won't know until they emerge from the glare, like 2025 UX-14 did, after closest approach. So the answer is, we don't know. There could be another one next week, next month, next year. We won't see it until it's close. Maybe too close. That's the reality we're living with until NEO Surveyor launches and begins operations." The press conference made headlines globally. Thousands of killer asteroids hidden in Sun's glare. Planetary. Defense admits blind spot. Next asteroid might not miss. The public reaction was predictable, fear, anger, demands for faster action, demands for more funding, demands for guarantees that couldn't be given. November 27, 2025. Dr. Mark Boslow, impact physicist at Los Alamos National Laboratory, gave a talk about what we'd learned from past near misses and actual impacts, the history that 2025 UX-14 almost repeated. "Let's start with Tunguska," he began. June 30, 1908, Siberia. An asteroid or comet about 50 to 60 meters across exploded in the atmosphere. The explosion was 10-15 megatons. 2,000 square kilometers of forest flattened. Trees knocked down radially from the blast center. If this had happened over a city, hundreds of thousands dead. But it was remote Siberia, mostly uninhabited. Few casualties, but enormous destruction. We got lucky. The object was small enough to explode in the atmosphere instead of reaching the ground, and it hit in one of the least populated regions on Earth. But what if it had hit 8 hours earlier? Earth's rotation would have put a major European city under the impact point. London, Paris, Berlin, St. Petersburg. Hundreds of thousands or millions dead. From a 50-meter asteroid. He showed the Barringer crater in Arizona. 50,000 years ago. Asteroid about 40 meters across. Struck at 12 kilometers, created a crater 1.2 kilometers wide, 170 meters deep. Everything within 10 kilometers vaporized or destroyed. This was smaller than 2025 UX-14. Much smaller. And look at the crater it made. Now imagine 2025 UX-14 hitting a city. 3 times larger. Much more energy. The destruction would be incomprehensible. Chelyabinsk, 2013, he continued. The one we all remember. Because it happened in the internet age. Because it was filmed. Because we saw the consequences in real time. Asteroid about 20 meters across. Exploded over Russia. 30 megaton airburst. 2,500 people injured, mostly from broken glass. 7,000 buildings damaged. Economic losses about $33 million. And this was just 20 meters. 2025 UX-14 is 7 times larger. Would cause 50 times more damage. Maybe more. And here's the terrifying part. Chelyabinsk came from the Sun's direction. Just like 2025 UX-14. We didn't see it coming. Professional astronomers didn't know it existed until after it exploded. Amateur cameras caught it, only because it happened to explode over a populated area in broad daylight. If it had exploded over ocean, we might never have known. Just a bright flash, a boom, some ships reporting strange blast wave. That's all? 2019, okay. Boslow said, pulling up another example. July 25, 2019. Asteroid 100 meters across. Passed at 0.19 lunar distances. Closer than 2025 UX-14. We detected it 24 hours before closest approach. 1 day. If it had been on a collision course, we would have had 1 day of warning. Not enough time to evacuate a city. Not enough time to deflect it. Not enough time to do anything except watch it come and pray it missed. And it came from the sun's direction. Again. Detected only when it emerged from the glare. By then it was already close. Already dangerous. Already too late to do anything if it had been a few 100,000 kilometers closer. He showed statistics, plotting known close approaches. Color-coded by detection time. Green, detected years in advance. Yellow, detected months in advance. Orange, detected weeks in advance. Red, detected days or hours in advance. Black, detected after closest approach. Most approaches were green or yellow. Those were the ones outside the sun's glare. The ones approaching from the night side. Easy to see. Plenty of warning, but a significant cluster was orange and red. And a few, including 2025 UX-14, were black. The failures. The near misses we didn't see coming. This is what we're up against, Boslow said. Most of the time our detection system works. We see asteroids coming. We track them. We predict their paths. We determine if they're threats. But 30% of the time, we're partially blind. And occasionally, rarely, but occasionally, we're completely blind. An asteroid comes from the sun, approaches without warning, and we don't know until it's too late. 2025 UX-14 reminded us of this vulnerability, reminded us that we're not safe yet, that our planetary defense system has gaps, and that closing those gaps is literally a matter of life and death for potentially millions of people. November 30th, 2025. Dr. Clemens Rumpf, planetary defense researcher at the University of Southampton, published a detailed impact analysis. What if 2025 UX-14 had struck Earth? The paper was both technical and terrifying. A rigorous scientific study of a catastrophe that almost happened. The paper started with impact physics. 2025 UX-14, 140 meters diameter. Mass approximately 2 million metric tons. Velocity at closest approach. 32 km/s relative to Earth. If it had been on a collision course, atmospheric entry would have occurred at approximately 30 km/s, accounting for Earth's gravity. Kinetic energy, 1 toward 2x mass, x velocity, squared. That's 900 trillion joules, 215 megatons TNT equivalent. For comparison, the largest nuclear weapon ever tested was Tsar Bomba at 50 megatons. This asteroid would hit with more than 4 times that energy. But unlike a nuclear weapon, all that energy would be delivered in one spot, instantly, with no warning, and no radiation. Just pure kinetic impact, explosion, blast wave, heat, crater, destruction. Rumpf modeled different impact scenarios, different locations, different angles, different conditions, building up a picture of the potential catastrophe. Scenario A, ocean impact, deep water, impact location, mid-Atlantic, 2,000 meters depth. Impact creates underwater explosion, excavates seafloor, creates cavity, water rushes back, forms tsunami. Tsunami waves, initial wave height 50 meters at 100 km from impact, propagating in all directions, reaching European coast in 3 hours, African coast in 2.5 hours, American coast in 6 hours. Wave height decreases with distance, but still 15 to 20 meters when reaching shore. Casualties, coastal populations at risk. Major cities, Lisbon, Casablanca, New York, Boston. Total population in tsunami zones, 50 million. With no warning, casualties could reach 5 to 10 million. Economic damage, $500 billion to $1 trillion. Scenario B. Ocean impact, shallow water impact location, Caribbean Sea. 500 meters depth. Closer to land, more destructive to coastal regions, tsunami waves, larger than deep water impact due to shallow bathymetry. Wave heights 80+ meters near impact, reaching Florida in 30 minutes, Caribbean islands in 10 to 20 minutes. No time for evacuation, no time for warning. Casualties. Caribbean islands devastated. Florida coast destroyed. Total population at risk, 40 million. Potential casualties, 10 to 15 million. Complete destruction of tourist infrastructure. Economic collapse of Caribbean economies. Global economic impact. Scenario. Sea. Land impact. Rural area impact location. Australian outback. Remote. Sparsely populated. Impact creates crater 2.2 kilometers wide. 450 meters deep. Everything within 30 km vaporized. Everything within 60 km destroyed by blast. Everything within 120 km heavily damaged by shockwave and ejecta. Casualties. Low due to remote location. Maybe 1,000, 5,000 if any settlements nearby. But enormous local destruction. Crater would be permanent, visible from space. Tourist attraction for millennia. Environmental effects. Dust ejected into atmosphere. Cooling effect lasting months. Agricultural impacts, but limited due to size. Not global catastrophe. Regional disaster scenario D. Land impact. Urban area impact location. Los Angeles metropolitan region. Direct hit on city center. Immediate effects. Everything within 30 km destroyed. That includes all of central Los Angeles, Beverly Hills, Santa Monica, Pasadena, Long Beach. 8 million people in immediate destruction zone. Buildings vaporized. Infrastructure obliterated. Ground zero crater 2.2 kilometers wide. Secondary effects. Blast wave destroys buildings to 60 kilometers. That includes all of Greater LA area. Another 5 million people in severe damage zone. Buildings collapsed. Infrastructure destroyed. Fire everywhere. Hospitals gone. Police stations gone. Fire departments gone. No emergency response capability. Tertiary effects. Shockwave breaks windows to 120 kilometers. That includes San Diego, Riverside, San Bernardino. Glass shrapnel injuring millions. 3 million additional injuries. Total casualties. 8 million dead immediately. Another 2 million dead from secondary effects. Injuries, fire, collapse. Another 5 million injured. Total of 15 million casualties. Worst disaster in U.S. history. Equivalent to 20 years of war casualties. All in one instant. Economic impact. Los Angeles economy is $1.1 trillion annual GDP. Complete destruction. National economic shock. Global economic shock. Recovery taking decades. Geopolitical consequences unpredictable. Rumpf's paper concluded with a stark assessment. If 2025 UX-14, Chapter 14, had struck Earth, it would have been the most destructive asteroid impact in recorded human history. Casualties would range from thousands to millions depending on impact location. Economic damage would range from tens of billions to trillions of dollars. The impact would be comparable to a major war or pandemic in terms of death toll and societal disruption. And we would have had zero warning, zero time to prepare, zero opportunity to prevent it. This is unacceptable. This must never be allowed to happen. We must close the blind spot. December 2025. The near miss of 2025 UX-14 triggered emergency funding discussions. NASA, ESA, international space agencies, governments worldwide. Everyone suddenly aware of the vulnerability. Everyone suddenly motivated to act. Dr. Meinzer's NEO surveyor mission was already approved and funded. Launch scheduled for November 2027. But could it be accelerated? Could they launch sooner? The hardware was mostly built. Testing was underway. But space missions don't rush easily. Every system must be verified. Every test must be passed. Skipping steps risks failure. And failure means the blind spot stays open even longer. We're pushing as fast as safely possible, Meinzer told a congressional hearing. But we cannot compromise mission success for speed. If NEO Surveyor fails because we rushed, we've lost years and billions of dollars. And the blind spot remains. Better to launch in 2027 with high confidence of success than launch in 2026 and risk failure. But other solutions were being proposed. Temporary solutions. Stopgaps until NEO Surveyor became operational. Dr. Ed Liu, former astronaut and director of the B600 Twide Chelyabinsk Foundation, proposed a small satellite network. We don't need a perfect solution tomorrow. We need an imperfect solution that's better than nothing. Put 6 small satellites in orbit. Cheap commercial hardware. Sensitive cameras. Position them to watch the sun's direction. They won't find everything, but they'll find some things. They'll reduce the blind spot, and they can launch within a year. The proposal was called SunWatcher. 6 CubeSats, each about the size of a shoebox, launched as secondary payloads on commercial launches. Total cost, $50 million compared to NEO Surveyor's $1.2 billion, not a replacement, but a supplement. Extra eyes watching the blind spot. NASA authorized the program in January 2026. Contracts awarded to 4 companies. First satellite launch, June 2026, full. Constellation operational, December 2026. 1 year from the 2025 UX-14 near-miss to having partial coverage of the sun's direction. ESA proposed something different. Ground-based solution. New telescopes optimized for twilight observing. Located at high-altitude sites, mountains, plateaus, above much of Earth's atmosphere, where they could observe closer to the sun without atmospheric interference. The program was called Dawn-Dusk Survey. 4 new telescopes, 2 in the Andes, 1 in the Canary Islands, 1 in Hawaii, all with specialized filters, all automated, all scanning the twilight sky every clear morning and evening, looking for fast-moving objects, looking for asteroids emerging from the sun's glare. Cost, $200 million over 5 years. Not cheap, but feasible, and could be operational within 2 years. Adding ground-based coverage to complement space-based detection, China announced its own program, Tianwang SkyNet, a dedicated infrared space telescope for asteroid detection, similar to NEO Surveyor but Chinese-built. Launch target, 2028. Not to compete with NEO Surveyor, but to supplement. Redundancy. 2 space-based detection systems better than 1. If one fails, the other continues. If both work, coverage is more complete. Russia proposed using existing military early warning satellites. These satellites watched for missile launches, infrared sensors, orbital positions optimized for watching Earth. But they could be reprogrammed. Software updates, new detection algorithms, looking for asteroid thermal signatures instead of missile plumes. Cost, minimal. Operational quickly. Not ideal, but better than nothing. The international coordination was unprecedented. 5 major programs, all focused on the same problem, all launched in response to one near miss. Politics and competition set aside in face of existential threat. When asteroid impacts don't discriminate by nationality, planetary defense becomes a shared human concern. February 14, 2026, Valentine's Day, 03:14 UTC. It happened again. Another asteroid, another close approach from the sun's direction. Another failure of detection. This one was smaller. 2026 CQ7, about 50 meters. Half the size of 2025 UX-14, but still dangerous. Tunguska size. City destroyer if it hit population center. Passed at 0.41 lunar distances. 157,000 kilometers. Closer than 2025 UX-14. Detected 8 hours after closest approach. The astronomy community was stunned. 2 major near-misses in 3 months. Both from the sun's direction. Both undetected until after closest approach. The problem was worse than they'd realized. The frequency was higher than expected. Dr. Chodas held another emergency briefing. We've had 2 significant close approaches in less than 3 months, both from the solar blind spot, both detected too late. This suggests the blind spot vulnerability is more severe than our models predicted. Either there are more asteroids approaching from the Sun's direction than we estimated, or we're even worse at detecting them than we thought. Possibly both, he updated the statistics. In a normal year, we might expect 1 close approach from the solar blind spot that goes undetected until after closest approach. We've had 2 in 3 months. That's 8 times the expected rate. This could be statistical fluctuation. Bad luck. But it might indicate a systematic problem with our understanding. Dr. Meinzer reviewed the detection circumstances for both 2025 UX14 and 2026 CQ7. Both had been dark asteroids, C-type, low albedo. Both had approached at very low solar elongation. Both had been moving fast, all factors that made detection difficult. But were there more like them out there? She ran simulations, modeling the population of near-Earth asteroids, estimating how many approached from the Sun's direction annually, estimating how many we'd detect with current capabilities. The results were sobering. We estimate about 50 asteroids larger than 50 meters pass within 1 lunar distance each year, Meinzer explained. Of those, approximately 15 approach from solar elongation less than 30 degrees. These are the hardest to detect. Our current ground-based surveys detect maybe 20% of them before closest approach. That means 12 per year pass undetected. Most are small. Most would burn up an atmosphere or cause limited damage. But 1 or 2 per year are large enough to cause regional catastrophe. And we're not seeing them until it's too late. 2025 UX14 and 2026 CQ7 are just the ones we found after they passed. There might be others we missed completely, objects that passed and we never detected at all. No pre-approach detection, no post-approach detection, just invisible bullets passing through our neighborhood while we're looking the other way. The briefing sparked renewed urgency. Congress held emergency hearings. How many more can we expect this year? What's being done? When will it be fixed? Dr. Lindley Johnson testified, the SunWatcher constellation launches in 4 months. That will provide some coverage. Dawn-Dusk Survey becomes operational in 18 months. NEO Surveyor launches in 20 months. By 2028, we'll have comprehensive coverage. But until then, we're vulnerable. Another near miss could happen next week. Next month, we won't know until it's over. The public reaction was fear. Asteroid apps downloaded by millions. People checking daily for potential impacts. Doomers predicting imminent catastrophe. Rational voices drowned out by anxiety. The threat felt immediate, personal, real. NASA published an emergency preparedness guide. What to do if asteroid impact warning is issued. Not comforting, but necessary. If an asteroid were detected on collision course with minimal warning, people needed to know their options. Evacuation routes, shelter locations, how to protect themselves from blast wave, from heat flash, from flying debris. The guide was downloaded 50 million times in the first week. Civil defense agencies worldwide adopted it. Schools taught asteroid drills, like fire drills or earthquake drills. But for space rocks, children practiced sheltering in place, getting away from windows, protecting their heads, the new normal in an age of known planetary vulnerability. June 18, 2026, 11:42 UTC, the first SunWatcher satellite launched. Piggybacking on a SpaceX Starlink mission, released into a 500-kilometer orbit. Solar panels deployed, cameras activated. Within hours, it was operational. Watching, scanning, looking for asteroids. 2 weeks later, June 30, 2026, the second satellite launched. Different orbit, different viewing angle. Together, they covered more sky, reduced the blind spot, overlapping coverage. July saw 3 more launches. By August 1st, all 6 satellites were operational. The SunWatcher constellation was complete. The network worked differently than ground-based surveys. It observed continuously. No day-night cycle, no weather, just constant surveillance. Each satellite scanned its assigned zone every hour, comparing images, looking for moving objects, transmitting detections to ground stations, automated processing, fast alerts. September 3rd, 2026, 06:23 UTC, SunWatcher 4 detected something. Fast-moving object, magnitude 17, solar elongation 22 degrees, deep in the blind spot where ground telescopes couldn't see it. The automated system flagged it immediately, sent alerts, calculated preliminary orbit. Dr. Davide Farnocchia at JPL received the alert at 06:31 UTC, 8 minutes after detection. He pulled up the data. One observation, not enough for solid orbit, but position and velocity gave rough trajectory. He ran preliminary calculations. His screen showed red. Impact probability, 12%. That's high, very high. Most asteroids have impact probabilities measured in fractions of a percent. 12% meant this was serious. Could be heading for Earth. Could hit in days or weeks. He immediately requested follow-up observations. Ground telescopes, space telescopes, anything that could see the object. Within 2 hours, 4 telescopes confirmed. The object was real. Designated 2026 RG3, and the orbit calculations were getting worse. Impact probability increased to 23% with additional data, then 41%, then 67%. Each observation refined the orbit, and the orbit kept pointing at Earth. Closest approach, September 17, 2026, 14 days away. Impact probability, 73%. Size estimate, 70 meters. Smaller than 2025 UX-14, but big enough. Tunguska class, 10-15 megatons if it hits. NASA activated the Planetary Defense Coordination Office emergency protocols. September 3rd, 12 UTC, 6 hours after detection. Press conference. Administrator Bill Nelson at the podium, grim-faced. At 06:23 this morning, our new SunWatcher detection system identified an asteroid on potential collision course with Earth. Designated 2026 RG3. Size approximately 70 meters. Current impact probability 73%. Potential impact date September 17th. That's 14 days from now. The room erupted. Reporters shouting questions. Cameras flashing. The first asteroid with high impact probability discovered in the modern era of planetary defense. The scenario everyone had been preparing for. Now real. Now happening. We're tracking the asteroid continuously, Nelson continued. Each observation improves our orbit knowledge. The impact probability may increase or decrease. We'll know within 48 hours if this asteroid will hit Earth. If it will, we'll know approximately where. We're working with international partners, emergency management agencies, civil defense organizations, preparing for all scenarios. But I want to emphasize, we detected this object because of SunWatcher. The satellite network we launched 3 months ago in response to 2025 UX-14. If we hadn't had SunWatcher, we would not have seen this asteroid until too late. This is exactly why we invested in closing the blind spot. And it's working. September 4th, 2026. More observations. Better orbit. Impact probability, 87%. Virtual certainty. It was going to hit. The refined calculations showed impact location. Indian Ocean. 800 kilometers south of Sri Lanka. Deepwater impact. Tsunami warnings issued immediately. Sri Lanka, southern India, Maldives, Indonesia, Thailand, Madagascar, East African coast. All coastal regions around Indian Ocean placed on high alert. Evacuations ordered for low-lying coastal areas. 14 days to prepare. Not much time, but infinitely better than zero warning. Dr. Rumpf ran impact simulations for the Indian Ocean scenario. 70-meter asteroid, 30-kilometer impact velocity, deep water. Results: initial tsunami wave 40 meters high, propagating at 800 km/h, reaching Sri Lankan coast in 45 minutes, Indian coast in 90 minutes, African coast in 6 hours. Casualty estimates, without evacuation, 5 to 8 million deaths. With successful evacuation, 50,000 to 100,000 deaths. The evacuation mattered. Desperately. Every person moved inland was a life saved. The evacuation was the largest in human history. 150 million people in tsunami zones, 14 days to move them. Some areas succeeded. Good infrastructure, organized government, buses, trains, highways, people moving inland, orderly, calm, public cooperation high. Other areas struggled. Poor infrastructure, weak governance, panic, gridlock, not enough transportation, people trapped in coastal cities, trying to leave, roads jammed, ports overwhelmed, airports full, chaos, international assistance mobilized, military transports, naval vessels evacuating people from coastal cities, cargo ships, cruise ships, everything that could float, moving people away from the coasts, away from the danger zone. September 17, 2026, 1433 UTC impact. The asteroid entered Earth's atmosphere over the Indian Ocean, traveling at 30 kilometers per second. Friction heated it to incandescence, visible for hundreds of kilometers, a brilliant fireball crossing the daytime sky. Then impact. The explosion was visible from satellites, a flash of light, then a rapidly expanding wave on the ocean surface. The tsunami forming, propagating outward, racing toward every shoreline. Warning systems tracked it, sirens wailing in coastal cities, final warnings broadcast. Move inland now. Tsunami arriving in 30 minutes. This is not a drill. Move now. The wave hit Sri Lanka at 1518 UTC, 45 minutes after impact. 35 meters high at some locations. Overwhelming seawalls, flooding coastal towns, sweeping inland, destroying everything in its path. But most people had evacuated. Most were safe. The cities were empty. The wave destroyed buildings, but killed relatively few. The wave reached Indian coast at 1603 UTC, 90 minutes after impact, 25 meters high. Kerala and Tamil Nadu provinces. Millions had evacuated. Casualties were in thousands, not millions. The evacuation had worked. The wave continued, reaching all Indian Ocean coasts within 8 hours. Maldives inundated, some islands completely submerged, but evacuated. Thailand, Indonesia, Madagascar, East Africa, all experienced tsunami. All had warning. All had evacuated. Final toll, 43,000 deaths, 2.1 million injured, $120 billion economic damage. Terrible. Tragic. Catastrophic. But far better than it could have been. Without warning, without evacuation, the death toll would have been 5 to 8 million. The detection system saved millions of lives, proved the concept, vindicated the investment. October 2026, 1 month after impact. The world was different. The asteroid threat was no longer theoretical, no longer something that happened in movies or happened to dinosaurs. It was real, recent, visceral. The 2026 RG3 impact became known as the Indian Ocean Impact. Memorial services held worldwide. 43,000 names read aloud. 43,000 people who died because a space rock hit Earth. Preventable deaths. If we'd had better detection, if we'd had more warning, if we'd invested in planetary defense decades ago, but also 7 million lives saved. Because we had detection. Because SunWatcher worked. Because 14 days of warning was enough to evacuate. The impact was both tragedy and triumph. Loss and survival. The worst and best of humanity's planetary defense efforts. Funding for asteroid detection increased globally. Every space agency, every government, recognizing the reality, the threat was real. The solutions worked. Investment was necessary. NASA's NEO surveyor received additional funding. Launch date moved up. November 2027 became August 2027. Acceleration possible now that consequences were proven. Resources materialized. Bureaucracy streamlined. Mission Critical Priority, ESA's Dawn-Dusk Survey expanded. 8 telescopes instead of 4. More sites. More coverage. Operational date. June 2027. 6 months earlier than originally planned, China's Tianwang accelerated. Launch, January 2028. 6 months earlier than planned. New missions proposed. Japan's Hayabusa 3. Sample return from potentially hazardous asteroid. Study composition. Understand structure. Better predict impact effects. Better design deflection missions. Russia proposed Tunguska 2. Space-based impactor mission. Kinetic deflector kept in orbit. Ready to launch on short notice. Hit incoming asteroid. Change its trajectory. Last-minute defense for objects detected late. For asteroids that slip through detection until they're close. The final backstop. The coordination was unprecedented. International Asteroid Warning Network expanded. Real-time data sharing. Coordinated observations. Joint impact predictions. Unified warning systems. Humanity acting as one species facing a common threat. The public response was complex. Fear, anxiety about future impacts, but also hope. Pride in human capability. We detected an asteroid 14 days before impact. We evacuated millions. We saved lives. We proved planetary defense works. Asteroid awareness became mainstream. Apps tracking near-Earth asteroids downloaded by hundreds of millions. Educational programs in schools. Public lectures packed. Everyone wanted to understand. To know the threat. To feel prepared. A cultural shift. From ignorance to awareness. From denial to acceptance. Yes, asteroids threaten Earth. Yes, impacts happen. But yes, we can defend ourselves. We have the technology. We have the capability. We just need the will, the investment, the international cooperation. And now we had it. Bought with 43,000 lives. Paid for in tragedy. But real, permanent, transformational. August 15th, 2027. NEO Surveyor launched from Kennedy Space Center. Flawless launch. Perfect orbital insertion. 3-month cruise to L1 Lagrange point. Arrived November 2027. Systems activated. Calibrations completed. Science operations began January 2028. The infrared telescope was revolutionary. Operating at 40 Kelvin. Cold enough to detect faint infrared emissions from asteroids. Positioned at L1. Between Earth and Sun, looking back toward Earth's orbit, watching for asteroids approaching from the Sun's direction, the blind spot. Within 6 months, NEO Surveyor discovered 2,147 new asteroids. Most small, most harmless, but 147 were larger than 140 meters. City killer size, previously unknown, hidden in the Sun's glare, now visible, tracked. Orbits determined. Impact threats assessed. None were on collision course with Earth in the next century. All were safe. But now we knew they existed. We could track them, monitor them. If their orbits changed, if gravitational interactions with planets altered their paths, we'd know. We'd have decades of warning. Time to deflect. Time to prevent disaster. By 2030, NEO Surveyor had found 8,121 asteroids larger than 140 meters. Combined with ground surveys, that was 94% of the estimated population. The catalog was nearly complete. Nearly every city-killer asteroid was now known. Tracked. Monitored. The blind spot was closing. Not completely. Small asteroids still slipped through. Objects smaller than 50 meters were hard to detect even with NEO Surveyor. But those caused regional damage, not global catastrophe. Important, but not existential. The goal was achieved. The gap was closed. The vulnerability was patched. We could now see asteroids coming from any direction. From the night side. From the day side. From the sun. Everywhere. All the time. Continuous coverage. Complete awareness. 2025 UX-14 could never happen again. An asteroid that size approaching undetected was no longer possible. The system worked. The defenses were in place. Earth was protected. July 2031, 5 years after the Indian Ocean impact. The anniversary had become International Planetary Defense Day, commemorating the lives lost, celebrating the lives saved, recognizing the importance of vigilance, of preparation, of international cooperation. Dr. Meinzer gave the keynote speech at the annual conference. 5 years ago, we didn't know if planetary defense would work in practice. We had theories, simulations, plans, but no real-world test. Then 2026 RG3 approached, and we detected it, tracked it, predicted impact, evacuated millions, saved millions. The system worked. Now, 5 years later, we have comprehensive detection, Neo-Surveyor, Dawn-Dusk Survey, SunWatcher, Tianwang, multiple systems, redundant coverage, global cooperation. We find asteroids months or years before potential impact. We have time to deflect, time to evacuate, time to prepare. The blind spot is closed. The gap is patched. The vulnerability is eliminated. We are no longer at the mercy of cosmic chance. We are defended, protected, aware. But vigilance is eternal. Systems must be maintained. Telescopes must be operated. Data must be analyzed. Warnings must be heeded. Deflection capabilities must be ready. This is not a problem we solve once. This is a commitment we maintain forever. Because asteroids will keep coming. They always have. They always will. Earth orbits in a cosmic shooting gallery. And we are the defenders, the watchers, the guardians of our world. Every generation must maintain the watch, must fund the systems, must take the threat seriously. 43,000 people died in 2026 because we weren't ready, because we hadn't invested enough, because we hadn't closed the blind spot. Their deaths were preventable, tragic, unnecessary. But they bought us this system, this awareness, this protection. Their sacrifice was not in vain if we maintain what we've built, if we never forget, if we never let our guard down. So today we remember the 43,000. We honor them. We commit to maintaining the planetary defense systems they bought with their lives. And we promise, never again. Never again will an asteroid hit Earth without warning. Never again will we be blind. Never again will we be vulnerable. We watch, we protect, we defend, forever. The audience stood, applauded. Not polite recognition. Real emotion, real commitment, real understanding that planetary defense was not optional, not negotiable, not something to defer or defund. It was civilization infrastructure, like water systems, power grids, communication networks, essential, permanent, necessary. The age of asteroid ignorance was over. The age of planetary defense had begun, and humanity had proved it could rise to the challenge, could cooperate globally, could invest in long-term protection, could act as one species defending one planet. Because that's what we were. One species, one planet, one fate. And now, finally, one defense. Sleep well tonight. The asteroids are still out there, still orbiting, still occasionally crossing Earth's path. But we're watching them, all of them, from every direction. Even from the sun, the blind spot is closed. The gap is patched. The vulnerability is eliminated. When you wake tomorrow, Earth will still be defended, still protected, still watched by systems that never sleep, by telescopes that never stop looking, by people who never forget that vigilance is the price of survival. Sweet dreams, defender of Earth. The watch continues, and we are ready. If this journey through humanity's closest call with cosmic catastrophe made you realize how fragile our existence is and how capable we are of defending it, hit subscribe. Every week we explore space threats that are real, immediate, and closer than you think. From asteroids to solar storms to cosmic rays. The universe is dangerous, but we're learning to survive it. Don't miss the next story of cosmic danger and human resilience.